All right, hello again, everybody. This video is going to review exam number 5, where I'll go through each question, provide a little bit of commentary. Hopefully you understand perhaps what you may have missed or reinforce some of the ideas behind questions you got right. So question number 1, this is one of our proton-deuterium exchange problems. We saw one somewhat similar to this during class in one of the examples. And this is where we use a specific type of reagents. We have now deuterated water and deuterated sodium hydroxide. So this will do hydrogen deuterium exchange with any acidic protons that are on the molecule. So the first thing to notice is that we have several different types of CH bonds. And of course, our job is to try to figure out which ones are the ones that are going to be acidic. So if we think about the pKa's of something like on a benzene ring, so we have a number of hydrogens on this benzene ring, these will all end up having a very, very high pKa. These are, around 40 or a little bit above. And sodium hydroxide just is not that strong of a base. So based off of that analysis, we can probably get rid of anything that has deuteriums on the benzene ring pretty quickly. And this leaves us with two different options. We have A and we have E. So E looks kind of strange because our double bond moved, and we'll see why that is in a second. A, on the other hand, it did deuterium exchange with the protons on the double bond, but it doesn't seem to touch the two hydrogens that are right next to the ketone. So if there are protons that we probably immediately will think will be acidic, it's going to be these two protons next to the ketone. So at that point, you could almost just conclude that A can't be the right answer either, so somehow it must be E. So let's look a little closer as to why E is the correct answer. When we go through the deprotonation event with sodium deuterium oxide, it'll take the hydrogen next to the ketone and we're going to make an enolate. And this enolate is actually an extended enolate where we have the enolate go across a longer pi system than usual. This means we can draw resonance structures where we can localize the charge on the carbon next to the carbonyl, or we can have the charge all the way at the end of this chain. This means that both of these carbons are nucleophilic, both the one that is immediately next to the enolate oxygen and also one that is farther away. In this process, we see that we can have deuterium exchange at both of these carbons that I labeled in green. And the main factor as to where the double bond ends up just has to do with overall stability. And so this double bond would prefer to be in conjugation with the carbonyl so that there's a more extended pi system. And this is where it ends up in the end. So at the end of the day, we end up with a deuterated methyl group at the end and a single deuterium in this vinyl position. But note that it did not deprotonate this vinyl directly. It did go through a normal enolate. For number 2, we have a series of molecules. We're asking which one will exist most in the enol form. So there's a number of carbonyl compounds. And if we remember the guidelines there, one, we need to have an enolizable proton. So this lets us get rid of C. There are no enolizable protons, so there's not really one to consider. B and E are both 1,3-dicarbonyl compounds, and these usually have much higher enol form than simple ketones or esters. So we can get rid of D. Esters have less enol character than a 1,3-diketone does because of the resonance interaction that they will lose along the way. So we can get rid of E. And then it comes down to A and B. And at first you might be thinking, oh, B will be the one with the most enol form, but really we never talked about A. If you draw out the enol form of A, it goes to an aromatic benzene ring phenol. So this is actually on our list of molecules that exist most in their enol form. Phenol was the number 1 choice, and it essentially exclusively exists in its enol, whereas something like B probably is at most around 76%, I believe is what we quoted in class. Number 3 is the Robinson annulation. We just changed things up a little bit because we added in an extra methyl to methyl vinyl ketone, and we have an ethyl instead of a methyl on this central carbon between the 1,3 dicarbonyl. So this will go through your normal Robinson annulation mechanism, where first we deprotonate, the soft enolate does a Michael addition into the ethyl vinyl ketone. Proton transfers will give you a new enolate that then can do an intermolecular cyclization onto one of the 2 carbonyls. And then finally, E1CB elimination, where these arrows will come down and kick out hydroxide, will give you choice A. Number 4 is a 2-step reaction sequence. So this is part of our Aldol Chemistry section. So this is the exact example we had on the slides where we have acetone and HCl. This is an acid-catalyzed aldol reaction, and we'll make a fully dehydrated product shown here. Then we have the nickel hydrogenation under high pressure. These were the new set of hydrogenation conditions that can reduce both double bonds and carbon-oxygen double bonds. So we'd expect this double bond to be turned into an alkane and this ketone to a secondary alcohol. And we see that option D is our answer there. If you use palladium on carbon without high pressure, then you would get A, where you just get the double bond reduced. If you use something like lithium aluminum hydride, then you'd get something like C as the answer. But we have the nickel hydrogenation, which does both for us at the same time. Question number B is a cuprate addition, where we have to know what type of reagent a cuprate is, and it is in fact a soft reagent. That means we're going to expect to have a 1,4 addition to take place. Note that cuprates do not add into ketones, they don't add into esters, so despite having an excess of this reagent, it still won't be able to react with any of those functional groups on the molecule. In addition, as soon as we do our 1,4 addition, the initial product will be an enolate, where we're going to have a negative charge on this oxygen, and so we wouldn't be able to have another attack on that carbonyl anyways. So this leaves us with our answer of B. Number 6 is our orbital questions, where we need to identify what the starting orbital is. We see an arrow coming from a double bond, so this would be a pi bond. So really, even if you can recognize what this answer is, B has to be the correct choice. So it's a pi to pi star interaction, and that leads us to the correct response. Oh. I don't know why I wrote that too quickly. Now we have number 7. We're looking for which of the compounds is the most acidic, and this is one which you really would be pretty hard to rationalize from first principles. But it so happens that each of these molecules are one of the ones from the pKa table that we are supposed to have in our memory banks, at least their relative pKs and ballpark figures. And so from that conclusion, we quickly get to C being the most acidic because it has a pKa of 13. We go to number 8. We have a dimethyl cuprate coming in again. So this is one of the cases where the first product will be dimethyl cuprate reacting with an acid chloride. Note that it doesn't do a further addition into the carbonyl. It simply will make a methyl ketone. Then we add in excess iodine and sodium hydroxide. These are our conditions for the haloform reaction. So after the first step, we're going to have a carboxylate salt that'll then be protonated with water to give us C, benzoic acid. Note that iodine really doesn't do anything on its own. We can't have any Friedel-Crafts reactions take place. Iodine on its own won't do things like iodinate benzene rings to do additions. So if you don't know anything else about this problem, and you know that iodine will not do Friedel-Crafts chemistry, we can quickly get rid of pretty much A B, D, and E. So from process of elimination, that might be another way to approach that question. 9 is one of our cyclization problems. So we have sodium ethoxide and ethanol. So I've numbered the carbons already. We know that the alpha protons will be acidic, so I drew in the carbon resonance form of the enolate just to be able to follow where the attacks take place. Whether you deprotonate it at carbon 1 or at carbon 4 as I have it labeled, it would actually give you the same product. So they end up being the same way, give you the same product from either side because this molecule is symmetrical. So this will first attack the ester to go to a tetrahedral intermediate. That tetrahedral intermediate will collapse to give you a 1,3 beta keto ester. With sodium ethoxide around, we will continue to deprotonate it, and 1 will be the product after the first step. And we don't even add in acid afterwards to regenerate the beta keto ester, because we can simply add in an electrophile directly to this enolate, and it will get alkylated, and we'll see that we're going to make a 5-membered ring with now a new methyl added into the molecule. So we see we have a methyl here, and it gets introduced there. Number 10 is asking which of the following is the least acidic. So when we go and look at our options, we can hopefully be able to get rid of B very quickly. It's a 1,3-dicarbonyl, so we know those are always much more acidic than other types of carbonyl compounds. From what we've seen in class so far, we've seen a lot of ketones and aldehydes versus esters. Esters are always less acidic than ketones and aldehydes, so we can probably get rid of these pretty quickly. And now we have A versus C. So we haven't explicitly talked about the pKa of an amide before. But what we have discussed is why is an ester less acidic than a ketone? And that had to do with the resonance structure of the ester and how when you deprotonate an ester, it loses this nice stabilizing resonance interaction. So this is an energetic barrier you need to overcome, because not only do you need to be able to make the enolate, you also need to be able to have enough energy to balance out the stability of that resonance interaction. If you use the same logic on an amide, this factor is actually going to be even stronger, because there's a much stronger resonance donation from the lone pair on the nitrogen of the amide into its carbonyl. That means that we're going to have an even bigger energetic penalty to overcome to make the enolate, and that'll make it the least acidic. 12 is a series of deprotonations with LDA followed by alkylation. The first one is with methyl iodide, and the second one has ethyl iodide. So along the way, we will deprotonate. The first step, there's only one place to deprotonate since it's symmetrical. Then we'll add in methyl iodide, and we'll make our initial alpha methyl ketone. Then we're going to react number 2 with LDA again, and now it's going to take the hydrogen on the other side of the ketone. That's because it's less sterically hindered. We will make this enolate, and it will be able to react with ethyl iodide afterwards. So this again is just an SN2-like reaction on the ethyl. B is a crossed aldol reaction question. Note that we don't have any enolizable protons on the aldehyde. We do have it on the acetone molecule. So we're going to be making the ketone enolate. And this ketone enolate, under basic conditions, we'll be able to add in to the aldehyde. Note that we don't have elimination in the final product. We still have our hydroxyl group. That means that we need to be doing it at reduced temperature. Another acceptable answer here I had was LDA, because LDA also only has one type of hydrogen that it can deprotonate. C is the reaction of an enamine with an acid bromide. So you see we have an enamine is a pretty nucleophilic neutral compound. We know that it's able to be alkylated and react with things like acid halides as well. Similar to enolates, its carbon is nucleophilic. We're going to use the lone pair of the nitrogen to push down into that pi system and attack the carbonyl. This will go through a tetrahedral intermediate that collapses, and then on workup breaks up our aminium to give this 1,3-diketone product with one methyl and one phenyl that comes from each component of the reaction. D is one of the aldol cyclization problems. We had a few different examples in class that we went through. And if we follow the logic or the approach we had in class, we know that this double bond originally came from an E1CB reaction. So if we imagine doing the reverse of an E1CB, this is hydrating this double bond, where this hydroxyl group is in the beta position. And now we need to imagine the intramolecular aldol reaction that had to take place. So again, we see that we had the nucleophilic carbon that would be from an enolate. It would have attacked this ketone. So we can also draw this enolate and the ketone there. Since this came from deprotonation, we need to imagine this in its ketone form. And this will get us back to this diketone molecule. Note that if you were to go back and count the number of atoms, we know we'd be making the enolate from the methyl. So this is one of our nucleophile. And we can just count down the ring. And we'll see that we still, in fact, do make a 6-membered ring in the process. An answer that I also accepted, because it is technically correct, but I would say that this is certainly not what I was looking for. The initial aldol product also technically is correct, because if you treated this with sodium methoxide and methanol, you would get that alpha-beta unsaturated ketone. So I think a couple people had that answer, and what can I say? It was correct. So number 13 is actually very similar to the question we had on the problem set, only we just use some slightly different reagents, and we do one less alkylation. So again, if we think about the malonic acid malonic ester synthesis, we're going to end up having a dianion equivalent of acetic acid. This allows us to do multiple substitution reactions. So we see that we have a methyl iodide appear in the product. We have our ethyl iodide. Its ethyl appears over here. We lose this whole fragment through loss of carbon dioxide. And the one thing to notice is that in this process, we will eventually lose this methyl as well, because it'll get hydrolyzed. That means that the methyl iodide starting material also needs to make an appearance at the very end of the reaction as well. So in practice, we would have sodium methoxide and methanol will give us the first alkylated product. Sodium methoxide, then ethyl iodide will give us the doubly alkylated product. Acid and heat, or you could do sodium hydroxide followed by acid and heat. As long as you hydrolyze the esters, it doesn't matter. We can get a carboxylic acid. But note that we need to turn this carboxylic acid into the methyl ester, so we can react this with methyl iodide and potassium carbonate. For this next problem, this is similar to the types of questions where we have some sort of aldehyde, we have a 2-carbon building block, and then we have a new product that has 6 carbons, so somehow we need to use 3 equivalents of acetaldehyde. If we try to map on where these things probably were, we can see that we probably had one acetaldehyde molecule here. That means we need to have another one right here. And then this last one came from yet a 3rd molecule. If we try to do retrosynthetic analysis, we see that the very left or right side of the molecule is in fact an aldol addition product. This means that we needed to do some sort of aldol addition between this aldehyde and this enolate. If you use something like LDA to make this enolate, the cross aldol should be fine. And now we need to figure out how to make this linear aldehyde chain. If we think about a normal just simple aldol condensation between acetaldehyde and itself, the initial product will give us a hydroxyaldehyde. So this is almost there, but somehow we need to turn this hydroxyl group into a hydrogen. And the easiest way to get rid of that hydroxyl group is to just do this with sodium hydroxide and heat. That way it will go all the way to the unsaturated compound. Once we have this unsaturated compound, then we can use palladium on carbon and hydrogen to selectively reduce just the double bond and not the aldehyde itself. So here I have the answer just written out, but I wanted to kind of talk through the process a bit more, so I wrote it again above. But you can see we can take sodium hydroxide and heat. This gives us our aldol product, reduce with palladium on carbon and hydrogen, make the enolate from LDA so that we have selectivity in this crossed aldol reaction, and then finally a workup with ammonium chloride. There were some answers on the exam that also were perfectly fine, and I think a similar number of steps, maybe one more, but this was their approach to making the butanal molecule. They saw this coming from the alkylation of the acetaldehyde enolate. So you could take acetaldehyde, reduce it with sodium borohydride, convert the alcohol to a bromide with PBr3, and this will give you the ethyl bromide fragment you need to do this alkylation, and then still would be finishing the problem in the same way. Question number 12 is our mechanism problem. And you see that we have what looks to be an overall Michael addition question, but we have HCl as the catalyst instead of the normal enolate, basic conditions. So we actually haven't done an exact mechanism for a Michael addition under acidic conditions, I believe, but we have seen aldol reactions under acidic conditions, and so this was the connection that hopefully we were able to make. So if we look at the nucleophile, it's already in its enol form. This is the form it will need to be in to react under acidic conditions. And this is like an okay nucleophile. It's not nearly as nucleophilic as an enamine. It's not nearly as nucleophilic as an enolate. So we need to have a really good electrophile in order to get it to react. And this alpha-beta unsaturated ketone is also just kind of like an okay electrophile. But since we're under acidic conditions, we can make this electrophile even better through protonation. Once it's protonated, now we have a very good electrophile. This lets our neutral enol nucleophile attack the 4 position because it is a soft nucleophile. And this also allows us to make a neutral product on the other side with a positive charge on this oxygen and avoid making the negative charge on this oxygen if we didn't protonate beforehand. From here, we can do a proton transfer where it'd be 2 steps. We take a hydrogen from this carbonyl and we protonate this carbon of the enol. And then finally, one last deprotonation will give us the final product. All right, that is all for exam number 5. I will post these solutions online. And if you're listening to this, you already know that, I guess.